When I say the words scientific notation, this is a way that we are able to express either really, really big numbers or really small numbers with a little bit of a different form, okay? It allows us to represent really big and really small numbers with some flexibility, okay? And when I say flexibility, that has to do with how many significant figures are found in our measurements, and we'll talk about that here in just a second, okay? All right. Scientific notation follows a general rule, okay, or a general kind of template, I guess I'll say. Okay, it's m times 10 to the n. Some number m times 10 to some exponent n. All right? And that template, in that template itself, our number right here has to be greater than 1 but less than 10. Greater than 1 but less than 10. So if I set up a number, something times 10 to the third, whatever this number is, has to be between 1 and 10. So I cannot have a number in scientific notation that says 53 times 10 to the second, right? Because is this number between 1 and 10? No, it's not, right? It's greater than 10. We want it to be written, instead of that, it would be 5.3 times 10 to the third. Okay? So that's the template for how we write scientific notation. Now let's dive a little bit more into what it means, right? Times 10 to the third means is the number that I'm trying to represent. I'm trying to represent this number. Is it bigger than 10 or is it less than 1? Is this number that I'm trying to represent here, by having a positive exponent, is it bigger than 10 or less than 1? Bigger than 10. It's a big number. I'm trying to represent a number that's big. In fact, I'm trying to represent this number. Here's where it is in scientific notation. This positive 3 means I need to move the decimal place 3 places to make my number bigger. So I'm trying to represent the number 5,300. Right? Does that make sense how that works? Okay. This positive exponent tells me that my original number is supposed to be bigger than 10. I don't like to teach if we move the decimal to the left or if we move the decimal to the right, that's how we know our exponent's positive, negative. I don't like that because sometimes I start with my original and sometimes I start with my new decimal and I don't like that rule. So the way I want you to think about it is if my original number is supposed to be larger than 10, my exponent should be positive. If my original number is supposed to be less than 1, my exponent will be negative. Okay, so let's do some practice here. Let's say that I want to express this number in scientific notation. Okay, I want that number to be put into scientific notation. Now, I need to check to see where my original decimal place is. Right here. But where does my decimal place need to go? Between what two numbers? Between the 1 and the 4, because I want mine to be between 1 and 10. If I put my decimal place here, now my number is 149. That's no good. If I put it here, it's 14.9, but if I put it here, it's 1.49. So now when I write it out, I would write 1.49 times 10 to the, and then I've got to decide, is my exponent going to be negative or positive? It's going to be negative because this original number, 0.0000149 is less than 1. I'm trying to represent a small number. So it's going to be times 10 to the negative, and then I decide how many spots did that decimal place move? 1, 2, 3, 4, 5 times 10 to the negative 5. Does that kind of make sense how we go about that? Okay? I'm not trying to memorize, move the decimal left, move the decimal right. I'm just looking at my original number. The number that I'm trying to represent in scientific notation is less than 1. So that's where I get the negative exponent from. The number 5 comes from literally counting how many spots did we move the decimal. And that was 5. Okay? Let's try another one. Let's say I want to put this number into scientific notation. All right, I want to put that number into scientific notation, and I'm going to give you an extra stipulation here. I want it in scientific notation with 2 decimal places. So when I say decimal places, what's that mean? With 2? No, if 2 decimal places, that means I need 2 numbers after the decimal, right? When I say 2 decimal places, I mean I want 2 digits to come after the decimal point. So let's figure out what needs to happen here. My original decimal place is right there. Where does it need to go? Between what 2 digits? 4 and 3. So it needs to go there. So that means I'm going to say it's 4.3 what? 4.39 times 10. 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 10th. Now, tell me, why did I make this 4.39 instead of 4.38? This digit right here causes that to round. Now, if I hadn't given you a specific number of decimal places to put in my problem, you could have put 4.3891, right? You could have put all the digits in that we know, but I asked you to write it in scientific notation with 2 decimal places. And so when I say 2 decimal places, I mean 2 digits after the decimal. Is that clear? Okay. I want you to see what this number means, okay? 4.39 times 10 to the 10th is really this number, right? If I expand this out, okay, give me just a second here. If I expand that out, it's 439000000. That's what it looks like. If I would have kept the number at 4.38 times 10 to the 10th, right? That's what it would have been if I would have kept it at 4.38, but I rounded it to 4.39 because this number is much closer to our original number than this. Do you see how that makes a difference? Right? When that's expanded out, I'm getting a number that's closer to my original. So that's what the rounding makes a difference for. It really does. Okay, it makes a difference. You'll notice, does anyone see a problem with putting numbers into scientific notation? What sort of problem do we encounter when we do that? Okay, we have to do that, but what's the problem in terms of our measurement? Are we losing anything by putting numbers into scientific notation? So we're losing some decimal places. We're losing some exactness of our measurement. Would we agree? Because we took this measurement that was here, and now we reduced it down to being 439 or 43 trillion or whatever. I don't know what the number is, but we reduced some of it. We lost some of the exactness of the measurement by putting it into scientific notation, and that's just how it goes. Okay, so when we do that, we lose some of the kind of the precision of our measurement. Okay? All right, I want you to try this one. I want you to put this into scientific notation with 2 decimal places. I want to put that into scientific notation with 2 decimal places. Okay, so what do you mean? What do I mean when I say decimal places? Numbers after the decimal, right? So you're going to have a ones place, then you're going to have a tenths and a hundredths place. I don't know how clear that vocabulary is for you, okay? Is that what we had? 1.44 times 10 to the negative 3. All right. Very good. Tell me what questions we have with scientific notation. Do you feel comfortable with the rounding of that last digit? Okay. Next class, we're going to get into some rules with math and making sure that we have significant figures done correctly. If I say significant figures, does that sound familiar to you? Or no? A little bit sometimes. It's usually new when we get here, but that's okay. So significant figures gives us rules about how exact our measurements need to be and all that kind of stuff. And so we'll have to do some manipulation with scientific notation. So I want to make sure we feel comfortable with that rounding. Okay?